Okay. For this unit, you want to be able to calculate molar mass. You want to be able to convert mole to mass, mass to mole, and being able to write the molecular equation. And being able to write chemical equations and balance it, and be able to do quantitative analysis of a chemical reactions. So the PowerPoints that I posted includes lots of example. So as a result, the PowerPoints includes a lot of slides, and it takes time. I just wanted to make sure that you have access to all those examples and you go over, but I would do a few of the examples again, just to make sure that the concept is clear, like how you find the formula mass for a given compound. Let's say you are given a compound CO2, and you want to find the mass for this. The example is given for H2O on this slide. You're trying to practice for CO2. You need to have access to the periodic table and count by look for atomic mass for each of the elements in the molecule from the periodic table. And when you look at the periodic table, the larger number, because you have two numbers, let's say for carbon, if you have 6 and 12, the one in greater value is the atomic mass. And you have one carbon, so it would be 1 times 12. For oxygen, you look at that number in the periodic table is 16 for each oxygen. Since you have 2 oxygens, it's going to be 2 times 16. So you are going to add this numbers, and it's 44. I'm rounding up to whole number just for simplicity. When you have for the exam, you have access to calculator, you do have access to the periodic table, 2 decimal places. If the question is determine the molar mass, 2 decimal places. If you need exact mass for it, 2 decimal places enough. You don't need to use more than that. So when you are taking this number, that number basically is AMU. And when you say AMU, basically you are giving the atomic mass of each element by the number of that element. You're adding all up. Since the scale expressed in the periodic table is based on atomic mass unit, so the first thing you do, you express based on the atomic mass unit, or AMU. But that's not a workable number. It's a very small number. What you do then, you are going to change that AMU to gram, and you express in the number in gram. That would be the mass for 1 mole is, or molar mass. So if you have the gram calculated AMU, change the unit to gram, that would be mass for 1 mole, or molar mass. What does molar mass or molecular mass, molar mass means is that is the mass for 1 mole. So molecular mass is the mass expressed in AMU. Molar mass would be the mass expressed in gram. So when you talk about molar mass, it means mass for 1 mole. Okay, so it's like something small, but but you need to know, because in everyday conversation you might use all these numbers based on molar mass, but you need to know the difference between the AMU value and the gram per mole value.
Can you just go over that one more time? It seemed a little confusing, because it looked like you were talking about the same thing, but it just seemed like there are 2 different components to that. So can you so when would you use AMUs and when would you use?
Okay. Whenever you are doing calculation of the periodic table, you're taking the numbers, you're bringing the numbers together using from periodic table. You would say, okay, that is AMU. But to change that to workable number, like a molar mass. So when molar mass is the question, if they tell you what's the molar mass, what does molar mass means? Like if you were in English class, if someone says what is molar mass, what's definition for molar mass? Molar mass is mass of what?
Mass of the mole.
Mass
Grams
of
over moles.
1 mole. Mass of 1 mole. Mass for 1 mole is molar mass. Okay, 1 mole, it's Avogadro's number of particles. So 1 mole is many, like this is a huge number. Avogadro's number is a huge number of the molecules. So when you say 1 mole of CO2 is 44 grams, you're talking about the molar mass, or mass for Avogadro's number of molecules of CO2. But when you say molecular mass, that means mass of 1 molecule. So molecular mass is mass for 1 molecule. 1 molecule only. That's the difference. So if it's a mass for 1 molecule expressed in AMU, but if it's molar mass is for mass for 1 mole, this is expressed in grams. Is that clear? So when you say mass for 1 molecule is made of atoms, you're adding mass of each atom. But if you're talking about the mole of something, you are talking about Avogadro's number of particles of that something. Like you have 1 mole of CO2, that means Avogadro's number of molecules of CO2 that exist in 1 mole of the CO2. So mass for 1 mole, when you learn about mass for 1 mole, how can you use that mass for 1 mole? Here's like an example of it, okay? How can you use that? So if you have the mass for 1 mole, what is the, okay, we already have this number here, that's good. So 1 mole, what does this mean? Molar mass, PbO2 equals 239.2. What does it mean? It means that mass for 1 mole of PbO2 equals 239.2 grams. Okay. Now, you can, sorry, just trying to change the color. This question says, how many molecules are in 50 grams of PbO2? So from the molar mass, you can change that to mole, okay? Mole is a mass mole, and mass mole particles. So if you have the mass, you want to convert to mole. How do you convert the mass to mole? What information do you need? You need the molar mass. Perfect. So if you have the mass and you want to convert to mole, you divide that by the molar mass, or you use the conversion factor. So if 1 mole of PbO2 equals 239.2 grams, then you can write that 1 mole over 239.2 grams, or 239.2 grams over 1 mole. So these are the conversion factors. You can use either one of them whenever it's needed. So if we have the mass and you want to change to mole, mass is in gram, which one of these should we use, A or B? Should I use A or B? If I want to go from mass to mole, I want to cancel the gram, okay? So this is like mass is expressed in gram. I want to cancel the gram, so I have to use A. So I'm going to start with 50 grams or 50.0 grams of PbO2 times 1 mole over 239.2 grams. By applying this first conversion factor, I have changed the mass to mole. This question is asking for how many molecules. That means it's asking for particles. If I want to go from mole to particles, what number should I use?
Avogadro's number.
Perfect. So if I want to go from mole to particles, because I want to just continue here, and I already know that I canceled the gram, I want to change mole to number of particles, I would use Avogadro's number. What is Avogadro's number? Avogadro's number, it's the number of particles per 1 mole of anything, okay? So if I have molecules of 1 mole of PbO2, then it would be molecules of PbO2. If I have element, it would be atoms. If I have ionic compound, it would be formula unit, because the particles are the smallest unit for a molecule. For a ionic compound is formula unit, for element is atom, and for molecular compound is molecule. Molecule and formula unit, they are used like interchangeably, but if you want to get like the exact term, if it's ionic compound, the correct term is to say what's formula unit. But when you say formula unit, then it's like students, they think of a new definition. It's basically the same thing as the number of molecules. So if you have the moles and you want to go to number of molecules, we have to write down conversion factor in a way that the mole is canceled. But 1 mole equals to 6.02 times 10 to 23 particles. And in this case, because we are dealing with PbO2, is going to be PbO2 molecules. So you have to be careful with this unit, because if the question was asking how many moles of, or how many atoms of oxygen you have, then you can't stop here. You have to convert to atoms of oxygen, or you have to specifically convert to atoms of the Pb. But since the question is asking for how many molecules, we have to, we can stop here. So the main part is to be able to relate mass to mole to particles. You see, mole is like a bridge. There is no way that you can jump this bridge. You have to cross the bridge. You cannot jump. There is no way that you can go directly from mass to particles. You have to first convert to mole, and then from mole you can convert to particles. But
Professor?
This bridge works both ways. If you have the particles, you can convert the particles to mole, and then from mole you can convert to mass as well. Yes, your question.
So from mass to mole, you would use 1 mole over 239.2 G.
Yes.
And then to convert from molar mass to mole, you would use 50.0 grams divided by, no, I'm sorry, 50.0 grams times 1 mole over 239.
Is the same thing, right? Is either dividing by the molar mass or multiplying by this ratio. This ratio converts the mass to moles, because by definition, when we have this number, molar mass of molar mass of PbO2 is 239.2 gram per mole. Okay, gram per mole. That means 1 mole of it is 239.2 grams. So we have that ratio. And then for Avogadro's, Avogadro says 1 mole equals 6.02 times 10 to 23 particles. it doesn't say what, specifies what particles, because it depends on you're dealing with molecular compound, you're dealing with ionic compound, or you're dealing with element. Okay, so did I
And
answer
one
your
mole,
question
one
based on
mole
the formula?
equals 239.2. Oh no, that's our PbO2.
Okay, 1 mole of anything, okay, anything equals 6.02 times 10 to 23 particles. That's like 1 mole of apple equals that number of apples. 1 mole of pencil is that many pencils. And
I
but
thought that was Avogadro's number though.
this is Avogadro's number.
And it's also what 1 mole equals.
Yes, Avogadro's number is the number of particles in 1 mole of anything.
Okay.
Yes, yes. So Avogadro's number is like Avogadro's number is expressed based on number of particles in 1 mole of anything, right?
Okay.
But when you are talking about molar mass is very specific. So molar mass of PbO2 is 239.4. Molar mass of CO2 is molar mass of CO2 is 44 grams.
Can you go to the previous slide so I can take a picture of it? Of your work?
Oh, do you think that no, it's recorded? I erased it. Sorry.
Okay.
Yes, I erased it, but it's recorded. Okay, the work is here on the next slide. I just wanted to make sure that I put it, I do write it there.
Okay.
So I show you the steps. I don't say, okay, here's the answer. Go figure out how we came up with that answer, okay? So I'm going to go back to example of CO2 that we were working with before. So CO2, we found 44 gram per mole. Okay, what does that mean? That means 1 mole CO2 equals 44 gram. That means 44 gram of CO2 equals 1 mole, and that equals 6.02 times 10 to 23 CO2 molecules. So when you say mole, okay, 1 mole, that's equals to the molecular mass expressed in gram. That's the mass. And then the particles is Avogadro's number of particle per mole. This is the molar mass. What does it mean? It means 1 mole equals that number in gram. So if you have 44 gram of CO2, in 44 gram of CO2, you can calculate and find that you have Avogadro's number of molecules. Okay, because you have to convert this to mole. When you convert to that mole, it's going to be 1 mole. And in 1 mole, in every mole, you have 6.02 times 10 to 23 particles of that. Or if it's a CO2 molecular compound, it's going to be molecules of CO2. So 1 mole of anything is 6.02 times 10 to 23 particles. 1 mole of atom, 1 mole of element equals to what? 1 mole of element equals to 6.02 times 10 to 23 atoms. 1 mole of compound.
And you would use that 1 mole element when you want to convert the atoms, like you were talking about the oxygen?
Okay, you see what is changing here is the substance that you're dealing with and the name for the particles. So smallest unit for element is atoms. Let's say you're dealing with iron, you're dealing with copper, you're dealing with sodium, potassium, anything that is just like uniatomic. So if you have copper, 1 mole of copper equals to 6.02 times 10 to 23 atoms of copper. But when you're dealing with compound, then that particles is going to be molecules. Molecule is the smallest unit of compound. Atom is the smallest unit of element.
To me, that's sort of confusing because I remember in the Newton lessons when you were trying to look for, say, the atoms in a sample of grams of one substance, you'd have to use the Avogadro's number to convert to the formula units, and then by that point you would multiply it by the empirical formula, I believe, or no, sorry, the molecular formula to get the atoms that you need.
To get the
So
atoms
multiply
you
it
need,
by
you have to use the ratio. You have to use the ratio. So let's look at this number that we have here, and I'm going to look at the examples that it's solved here. So we already, in this case, we already have the molecules of PbO2, right? In
Right.
order to get the molecules of PbO2, you convert the mass to mole, and then from mole to
Right.
Avogadro's number. But when you get to here, you have to specify this is the molecules of PbO2, and it's not atoms of Pb. If the question was asking for how many atoms of Pb you have, then you would multiply this by a new ratio. You would say 1 mole of PbO2 has 1 mole of Pb. 1 mole of PbO2 has 2 moles of oxygen, right? And then when you have
Right.
this ratio, you can also say 2 oxygen per 1 PbO2. So this is the ratio is what you are using to go to the moles of the atom, or the number of particles of the atom.
Yeah, so I understand that, right? I'm more so asking, like, if you have, say, the molecules that you circled there, right? So the 1.26 times 10 to the 23rd, you have that, right? If you wanted to, say, find the atoms of that compound, what would you do?
Atoms of the compound. So it just says generally atoms of the compound. It doesn't say how atoms of Pb or oxygen. Then okay, if it doesn't say atoms of Pb or atoms of oxygen, then you would say for every molecule of PbO2, you have 3 atoms. Then you multiply that by 3. Out of those 3 atoms is 1 Pb and 2 oxygen. So atoms, you have to, it has to be clear. So we have plenty of examples. Let's look at some of the examples, and then if that matches to your question, you stop me. If not, then you would, then we will talk about the other, possibility. And then we also have the percentage, which by definition percent is like, if it's a percent mass, it's mass of the part divided by the whole, or mass of the element. If it's percent composition, is going to be mass of the element over mass of the compound, mass of the element over molar mass of the compound. So it's in general is like part over whole times the 100%. So if you are given a so this is the solved problem. Again, it may not help you a lot for I'm trying to look for blank page so I can use the new example. Let's say you want to find the percent composition for percent comp for CO2. Okay, maybe it's one of the solved problems. What is basically, if you're trying to find percent composition, saying what is the percent of carbon and what is the percent for oxygen? That is percent composition. So if they don't give any numbers, you are going to assume that you have 1 mole of CO2. And if you have 1 mole CO2, in 1 mole CO2 is going to give you 1 mole carbon and 2 mole oxygen. Be careful, you don't want to say 2 mole of O2. Because if you say 2 mole of O2, that's 4 oxygen. You either have to say 1 O2 or 2 mole of O. So we know that 1 mole for CO2 is 44 grams already. We did this example. Then 1 mole of carbon is 12 grams. So we have these numerical values. And 2 mole of O is 2 times 16, and that equals 32 grams. So we know these masses. Now, if you want to find the percent composition, you are going to say percent for carbon is going to be mass of carbon, because we assume that we have 1 mole. So after 1 mole or after 44 grams, 12 grams would be carbon, and divide by total, which is 44 grams, times 100%. And that gives you percent of C. Percent of O is going to be 32 grams. For every 44 grams, you get 32 grams of okay, so this is just to specify that we are dealing with the percent oxygen. Okay, you don't have to, for percent composition, because it's not going to cancel, you don't have to write it, but I was just trying to clarify that this is for percent of the oxygen that you're dealing with. So you have times 100, that the 100%, that would give you the, whatever the number is going to give you the numerical value for percent of the oxygen. So this might help you with your questions that you had earlier. 1 mole of CO2 has 1 mole of carbon. So 44 grams of CO2 has 12 grams of carbon and 32 grams of oxygen. So you are using, if it's expressed in mole, you are using the mole value. If it's expressed in mass, you are using the mass value. So that's for percent composition.
Professor, is that the like universal like law of like one car like CO mass equals 44 grams?
1 CO2, 1 mole of
C
CO2.
The one, okay.
1 CO2 equals 44 grams. Where did you find that? We actually looked up that in the periodic table.
Okay.
Because when we were adding the masses of carbon and the oxygen, we looked in the periodic table. In periodic table, we have 12 grams for every carbon. Since we have only 1 carbon, we say times 1. And then for oxygen, 16 grams is for oxygen. This is coming from periodic table. And 16 grams times 2, because we have 2 oxygen in CO2. When you add them together, that is 44 grams per mole, okay, per mole of CO2. So every mole of the, so periodic table, it gives you the atomic mass expressed in AMU, but when you add those AMU and you cross the AMU, you change that to gram, that changes the mass for 1 mole. So from periodic table, you find mass per molecule, but in the in our calculation, we change the AMU to gram, and that would be mass per mole. Because molecule is not a workable number. Mole is a workable number. So we have to change that to gram so we can work with them.
On the periodic table, it's mass per molecule?
Per atom. And then when you add them together is the mass per molecule. Yes. Let's see here. When you find this number, when you find this like a 2 or 3, you can say 1 gram per mole, but if it's not expressed per mole, per molecule is going to be 2 or 3 AMU. but you find the AMU and you convert that to gram in order to say that's the mass for 1 mole. And then when you're finding the mass, percent mass for element or elemental analysis, you would say mass of that element in this compound. You cannot say 35 for chlorine because periodic table shows 35 for chlorine in this example that we have on the slide, because for this molecule, for every mole of C2Cl4F2, we have 4 chlorines. So percent of the chlorine is like 4 per molecule. So that's why you have to say 4 of the 35. So you have 4 times 35.5, that's the mass of the chlorine. And then the total mass is the mass of the whole molecule expressed in gram. So molar mass is the mass of the compound expressed in gram. Any question about this new example? Percent composition for calcium chloride, that means find the percent of calcium, find the percent of chlorine. And since you have only 1 calcium, mass of 1 calcium is 40 grams, but mass of chlorine, you have 2 chlorines, 2 times 35 is going to be 70. So total mass or molar mass is 110, calcium is 40, divide 110, and chlorine is 70, divided by 110. If you add these 2 numbers, if you have only 2 elements, if you add these 2 numbers, it should basically add to 100%. So if you're 100% sure that you did the calculation for mass of calcium properly, you can say 100 minus 36.11, that can give you the percent of Cl also, if you have only 2. Because if you have only 2 elements, total percentage should add up to 100. Okay, benzaldehyde, do you have any questions about this problem here? If you have the percent composition, how would you find the mass of that?
Will the chemical formula be given, or are we
Yes.
supposed to know what benzaldehyde?
No, the formula would give it.
Oh, okay, okay.
Yes.
Oh, there it is.
Yes.
Where? Okay.
Would you divide by 100 first?
Okay, see, like you didn't basically have to have the formula, whatever the formula is. If you have 100 gram of that, so when they say percentage, okay, when they say percent of the carbon is 79% carbon, okay, whatever it is, in every 100 gram of benzaldehyde, you have 79.2 gram of carbon. So if you say 10% alcohol, what does it mean? It means that in every 100 gram, okay, every 100 gram contains 10 gram of alcohol, right? 10 gram of alcohol, or 10% salt water solution. Means every 100 gram of the salt water solution contains 10 gram of salt and 90 gram of water. So if you say 79.2% is carbon, for every 100 gram of benzaldehyde, 79.2 gram of that would be carbon. So now that you have only 19 gram of, you want to know that what is the mass of the benzaldehyde that would have 19.8 grams of carbon. So you can write the percentage in a fraction form as the conversion factor. And if you have the conversion factor, it goes both ways. 79.2 gram carbon for 100 gram of benzaldehyde. Okay. So if you are given mass of carbon, and you want to go to mass of benzaldehyde, you would use this one. But if you are given mass of benzaldehyde and you want to go to mass of carbon, you would use the way that you would cancel mass of benzaldehyde. So basically you are using as a conversion factor. This was a question that you had earlier, like if you have the moles of the molecule, how do you find the mole of the atom? Basically, you are using the ratio. So let me just make this clean so you could see, let's say up to here, whatever the calculation was, you end up with the moles of H2O. To go from moles of H2O to moles of H, you are using ratio of element per molecule. For every H2O, you have 2H. For every H2O, you have 1 O. So you can find this, how many moles of H you have. So if you have 10 moles of H2O, that would be 20 moles of H, right? 10 moles H2O, it gives you 20 mole H. You see that? 10 mole of H2O gives you 20 mole of H. But if you have 10 grams of H2O, you cannot say you have 20 grams of hydrogen in 10 grams. The mass doesn't work directly. The mass, you have to first convert to percentage, or you have to convert to the, you have to use either percentage or you have to use the mole. You cannot just say mass to mass. 10 grams of water doesn't have 20 grams of hydrogen, but 10 mole of H2O has 20 moles of hydrogen, because hydrogen is lighter than water. So that is possible. So you have to cross that bridge of mole first. You have to convert to mole first and understand that if it's a molecule, if you're looking at one molecule of H2O, that would be 2 atoms of hydrogen, 1 atom of oxygen. But if you're talking about 1 mole of H2O, it would be 2 moles of hydrogen atom and 1 mole of oxygen atom. So it's like being able to read the equation.
For the exam, we don't have to know the conversion factor of liters to gallons, do we?
I have usually the conversion factors, like specifically they are part of the exam 1. And then if it's something that is not everyday use, I give the numerical value, the equivalence.
Okay.
Okay, how would you solve this problem? How many grams of sodium are in 6.2 grams of NaCl? So you have the mass of the compound. You want to find the mass of element. So first you need to know the percentage, or you need to know the moles, right? Mm. So you have to get the percentage for, we are looking for sodium. So percent of the sodium is 23. I'm just going to round up, 58.5. So gram of sodium, and then this one would be gram of total. This is the part, element, molecule, times 100%. So if we have this number, and can someone give me that number quickly? I think it's on the next slide, but I don't want to. Okay, so if you want to get the, I don't have the number unless you give me the number. So we have the percentage of the sodium. Anybody can give me that number quickly, or you want me to?
39.1. I mean 39.31.
Thank you. 39.3. 3. Okay, 39.3%. Okay, so what does that mean? That means 100 gram of NaCl is going to have 39.3 grams of Na. So now we have a workable, like a conversion factor here. So the question is, how many grams of sodium are in 6.2 grams of NaCl? So we can use this conversion factor. So we always start with the given. What is given here is a 6.2 gram of NaCl. What should be my conversion factor? Should I write 100 over 39 or 39 over 100?
100, or sorry, 39 over 100.
Because I want to cancel the mass of NaCl, right? I want to end up with mass of Na. So 39.3 gram Na over 100 gram of NaCl. So the units of gram NaCl is going to cancel. You do the math. When you do the math, is going to give you the mass of sodium only. So can you tell me what's that number? That's like 2.43, right? Or 2.44. What would
Yeah.
be units here?
2.44.
Okay, 2.44. What's the unit?
Gram, or no,
Gra-
sorry, not a gram.
Gram of what?
Na.
Is it grams? Oh, I see. Okay.
Is the
Yeah,
gram
the
of
Na.
Na. Does
Yeah.
it make sense?
Yeah.
6 gram of NaCl has 2.44 gram of Na. Now, if you did all your calculation and you come up with like 8, then it doesn't make sense. If you have 6 grams, 6.2 gram of NaCl only, you cannot have 8 gram of Na. So you can always go back and make sure the final answer make sense. So if it's 2.44 gram Na, and then the rest or the difference from 6.2 is going to be the mass of Cl, which is not the question asked in this. Empirical formula is, that was a question earlier. To find the empirical formula, you have the percent composition. If you have the percent composition, you are going to assume 100%. So you say you have 100% or 100 gram, because from the percent, you cannot go to mole, but from mass, you can go to mole. So empirical formula is the lowest whole number ratio of number of moles of atom in a molecule. So by definition, so what if you have like a H2O, that's the lowest ratio that you can go with the whole number. Because if you divide this by 2, you end up with H1 and 0.5, and this is not allowed. 0.5 is not allowed. So empirical formula is going to be same thing as the molecular formula for H2O, and its empirical formula is H2O. Now, if you have H2O2, you can convert that to H1O1. This is called lowest whole number ratio of the atoms in the molecule. So this is the actual ratio. Molecular formula shows actual ratio. Empirical formula shows lowest ratio. If you want to go from empirical formula to the molecular formula, you have to multiply that by an integer, and that is the n value. In this case, we already know, because we have the empirical and we have the molecular, is going to be 2. So you multiply the empirical formula, the subscripts only, by 2 to go to the molecular formula. So if you have H1O1 as the empirical formula, you want to multiply by 2 times, or when you say n equals 2 is better. So n equal 2, so you are going to multiply that. H1 times 2 is going to be 2, and O2. The relationship between the empirical formula and molecular formula, the ratio of the elements in a molecule stays the same. It's like a 2-2-2, same thing as 1-to-1 ratio. The mass for empirical formula and molecular formula is related. Is not the same, but it is related. Related by what? Related by the N value. So if you have 34 grams here, for H2O2 is going to be 17 gram for H1O1. The mass for empirical formula times N value, it gives the mass for molecular formula. So if you have the molecular formula and you want them, if you have the empirical formula, you want to find the molecular formula, you need to know what's the value for N. So you have to find the relationship between them, find the value for N, and then decide. So if you have the empirical formula for H1O1, and you know the mass is 17 gram, and you don't know that this is a H2O2, you don't have the value for N, but you have the mass. You say, okay, if this is 34 for molecule and 17 for empirical formula, then it must be double. So N can be 2. So that's how you find that, that ratio, the N value. So steps are given here. You have done enough practice. So you want to start with gram. If percent is given, just assume that you have 100 gram. So if it's like a 50-50%, that means if you had 100 gram, 50 gram would be this, 50 gram would be the other one. Then you start with the gram of each element and you convert to mole. How do you go from gram to mole? You need your periodic table. Okay? For each element, you want to find it. And when you have it, you are going to divide that by the lowest number to get the smallest number of moles for each of the elements. So when you have the smallest, you want to make sure that is a whole number. And if it's not a whole number, you work with them to make it whole number. So if you have like a H1 and then 0.5, this is not a whole number. So how can you change this to whole number? You multiply both of them by 2. That is going to go to H2O. But if you have let's say A1 and then B is 0.33, you multiply both numbers by 3 in order to go to whole number. So it's going to be A3B1. So you just have to see what is the ratio, and then you work with those numbers in order to go to whole number ratio, because that's a whole number ratio. So if you have this percent composition and you want to go to empirical formula, was that your question? So I can work on this problem, or you had a different question? Or you had the empirical and you wanted to know the molecular? Someone had a question earlier. So the first step on this, it would be to change the percentages to gram, because we assume that we have 100. So second, you are going to change that to mole for each element. So you have to cancel the gram, and you are using periodic table to get this number. You're using periodic table for the hydrogen to get the number is 1 gram of the hydrogen. So 1 mole of C, and this 1 mole of H, and 1 mole times 1 mole of O over 16 gram of O. Then you're canceling the numbers. If you can give me these numbers quickly. For carbon, what do we have? For carbon is 5, right? Carbon is 5. Hydrogen is 4.4, and oxygen is what?
35.45.
2.2?
16. Yeah, 2.2.
2.2, and then for oxygen, we actually had 5. Okay. So we have to divide all these numbers by 2.5.
Professor.
Yes.
So 60% divided by 12, is it 0.6 divided by 12, or is it 60?
No,
60.
it's 60. Yeah.
60. You are just going
You're
to
using the percent, yeah.
percent. So you cross the percent and you change it to gram.
Although admittedly that's still sort of confusing to me. Like for example, the one where we took the grams of sodium chloride and then found sodium in that compound, it was kind of just weird that we divided the molar mass of the Na and then divided it by the 100 grams. I don't know. To me, that's just kind of weird. Not sure why you can do that.
Okay. So that was like from the percent to go back to the actual mass, or from the percent going to empirical formula.
So that was here. Wait, let me pull it up. 'Cause I took
Okay,
a picture.
I'm going to go to the next step while you're looking for that. So we divide this, all of them, by 2.2. That gives me 1, 2, and this would give me what? 2.27. So now I have this ratio of 2.27.
Why 2.2?
Is not, because that was the smallest number. Or maybe 35 is different. 35.53 divided by 16, what number that gives? 2.2.
Oh,
okay.
yeah, no, it was 2.2.
Okay. 4.48, maybe it makes a difference here. 2.22. Okay. The smallest number, you divide by the smallest number to find the lowest ratio, and then hydrogen is 2, and you have the other one, oxygen, as 1. Is this the empirical formula? Can this be expressed as empirical formula?
No.
No, because we have decimal. And if you end up with 0.5, you multiply everything by 4, okay? You multiply by 4 in order to change the 0.25 to whole number. So it's going to be, C is going to be 2.25 times 4.
Right, 9.
9.
Mhm.
And then hydrogen is going to be 8, and oxygen is going to be 4. So you have, this is going to be empirical formula. Okay, empirical formula. So you just follow the steps. Convert to gram, convert the gram of each element to mole of each element, divide all moles of element by the smallest mole number for the element. You find the lowest ratio, but your lowest ratio must be whole number. If it's not a whole number, you work with it and multiply by n value.
Oh,
get,
actually, I see what. So when I was pulling up the other example, sorry, I am interrupting. I figured it out basically for the.
okay, perfect. So empirical formula, we know that is the X, Y, and Z. Those are the numbers that we're trying to find. So this is going to give you a multiple, slide. That's why it's long, but we're just trying to get the, steps to make sure that you know the steps. Okay?
Are these slides given, or is this one of the slides that you put
No,
together?
it's given. All of them are given in the PowerPoint I included. It's
Okay.
posted in Unit 5. I did post this a little earlier, so I was hoping that you have access to it.
I didn't get a notification for that, oddly.
I have no idea.
Usually when you post it, like because I remember right before the last exam we had.
But do you see it now? Maybe you were online at that point. And do you see it now? Did you see it later or you didn't see it?
I
don't-
didn't see it.
don't
Yeah.
see-
Is it up? Okay.
It probably is now, I would imagine. I just didn't get a notification that it was up, so I
No,
didn't
I
know.
posted both, yes, part 1 and part 2. So another example, like if you have the percent empirical formula of that which contains 72.4% of iron, and the rest is oxygen. So 100 minus that is going to be oxygen. So just sometimes the information are given like indirectly. So as long as you have the percentage for both, you cross the percent sign and you change that to gram. Then you go from gram to mole. Going from gram to mole, you need the periodic table. You divide by the atomic mass from periodic table. Then you have the mole. You want to make sure that you divide by the smallest number to get the mole ratio. If the mole number ratio is not whole number, you have to make sure it is whole number. If it's not whole number, you multiply by, like if here you get like 1.33 is not a whole number, you multiply both of them, not just one, both of them by 3 in order to get the, okay. Molecular mass divided by empirical mass is the multiplying factor, N, okay? Multiplying factor N is the molecular mass. So if you have the molar mass and then empirical mass. If the empirical formula is given or the empirical formula is calculated, and you will be given the molar mass. Molar mass, if you don't have the molecular formula, you cannot calculate the molar mass. With the percentage, you cannot calculate molar mass. You can calculate, you can find the empirical formula, but you cannot find the molar mass. So molar mass should be a given number. So when you find the empirical formula, you find the empirical formula mass, okay? Empirical formula mass, and you divide the molar mass by the empirical, you find that N value. So in this example, if we have the empirical formula already, we have the empirical formula and the molar mass is 86, find the mass for empirical formula to be 43. So molar mass is double the empirical mass. So N value is 2. Since N value is 2, you multiply all these by subscripts by 2, and that would give you C4H6 and O2, and that would be the molecular formula. Okay, any questions about this? Next example, if you already have the molecular formula, I'm sorry, you have the empirical formula and you have the molar mass. Any questions? Have to find the molecular formula. Okay, percent composition, if it's given, we can calculate the empirical, we can find the empirical formula if the percent composition is given. Or solve problems. So when you go to chemical equations, like being able to read chemical equation, it is very, very important for you. So when you read this chemical equation, if this chemical equation is given to you, you can read based on number of moles or number of molecules. Okay. So if I read this equation, I can say 1 mole of CH4 plus 1 mole of O2, it yields or gives 1 mole CO2 plus 1 mole H2O. So that's what I'm reading. Another way of reading is going to be based on the molecule. It says 1 molecule of CH4 with 1 molecule of O2,
It's
it would
not balanced.
is not balanced. That's how I'm reading, just reading the, okay? Reading the equation. 1 molecule of CO2 and 1 molecule of H2O. So when you have a chemical equation, being able to read, if there is no number, you place 1 to read the equation. If the equation is not balanced, like this, that you notice that it needs to be balanced. First, you have to be able to read the equation. Second step, being able to count the elements in a compound, okay, and add them up. How many oxygens we have on the product side? Based on the given equation, not balanced, but how many oxygen you have on the product side?
3.
You have 3, okay, perfect. How many oxygen we have on the reactant side is 2, basically coefficient times the subscript. How many hydrogens we have on the reactant side is 4, because only this compound has hydrogen. The other compound doesn't have on the reactant side any hydrogen. On the product side, it shows that we have 2. So we know this equation is not balanced. In order to balance the equation, you count the atoms on both sides, and you want to make sure that they are the same number of atoms on both sides. Basically, that is going to, based on the law for conservation of the mass is not destroyed, it's changing from one form to another form, and we have to have the same number of atoms on both sides in a balanced equation. This type of reaction is called the combustion reaction. For a combustion reaction, you should balance the carbon from left to right, hydrogen from left to right, but oxygen from right to left. This is just a trick that is going to, it works either way, but it's going to make it faster. So how many carbon I have on the reactant side? It's 1, right? I have 1 carbon, and I have 1 carbon on the product side. It is balanced. I leave the carbon alone for now. I'm not sure if it's going to stay this way or not, but for now, I'm going to leave it alone. Then balance the hydrogens. I have 4 hydrogens on the reactant side, but I have 2 hydrogens on the product side. In order to make this 4, I cannot change this to 4 because that does not exist. What I can do, I'm allowed to do, is only to change the coefficient. So I can play with the coefficients only. What number should I add to this coefficient in order to give me 4 hydrogen? Because I already have 2, and when I'm counting, is like the coefficient times the subscript. So 2 times 2 is going to give me 4. Now I have 4 hydrogen and 4 hydrogen. Then balance the oxygen. I have 2 oxygens from CO2, and how many oxygen from H2O?
2.
2. The coefficient applies to every element in the molecule. So 2 times 1 is 2. I have 2 oxygen and 2 oxygen, that's 4 oxygen. 2 on the reactant side. In order to make it 4, I can only add coefficient in a way that if I multiply by the subscript, it adds up to 4. I cannot change this to 4 because that does not exist. So now that you have a balanced equation, you can read it one more time. It says 1 mole of CH4, 2 moles of O2. It gives 1 mole of CO2 and 2 moles of H2O. When you have a balanced equation, that becomes the recipe, or any number dealing with when you're dealing with the balanced equation, any calculation or quantitative analysis is known as a stoichiometry of that reaction. So balancing, if you don't have a balanced equation, your recipe is not good. Like if you know that food, the ingredients for the food is salt and salt and water, meat and the other two. Now, if you don't know how much salt, you cannot come up with the food that is edible or eatable. Then you can get that, too salty or no salty enough or not enough salt. So you have to know the recipe. You need to know the quantity. The good thing is, like, as soon as you have a balanced equation, you can relate the reactants to product based on number of moles, based on number of molecules, based on the mass. So you can do all sort of calculation and quantitative analysis starting with the balanced equation. The key is a balanced equation. So you could have the mole ratio. So we had here 2 and 2. If 2 moles of methane is used, how many moles of water would you get? Based on this equation. If 2 moles of methane is used, number of moles of water would be? 4. If you use 3 moles of methane, you get 6 moles of H2O. If you use half a mole of methane, 0.5 CH4 will give you 1 mole H2O, right? Because this ratio is a fixed number. The relationship between moles of H2O to moles of CH4 is always 2:1 ratio. So you can use this, the coefficient as the mole ratio or number of particles. You could also use this like in a gram, but it's best to learn based on the mole, convert everything to mole, and then work with the mole. Because if you have the mole, number of moles, then you can convert that into gram later. Let's say if you start with 2 moles of CH4, how many, the question is how many moles of H2O? Second question would be how many grams of H2O? And I'm going to erase the half here, so we know that we are only working with the 2 moles. So how would you find out how many moles of H2O? You use the coefficients. So you start with 2 moles of CH4 and you multiply that by 2 H2O for every 1 CH4. The next question, it says how many grams? I already have the moles of H2O. So, and I know that 18 grams is mass for 1 mole of H2O. Then I can convert to mass. But knowing that the relationship between mass and mole and vice versa using molar mass, that's the key. Being able to balance the equation, it's very important, because if your equation is balanced, all your numbers are going to be invalid. And then you can use the mole ratio of reactant to product, 1 reactant to another reactant, 1 product to another product. Let's say in this equation, pay attention to this question. I think you have this question on the exam. Let's say, or similar one. Let's say in this equation, if 2 moles of CO2 is produced, how many moles of H2O is going to be produced?
You're gonna multiply it by the ratio. So you'll take, you have 2 moles of 2 moles of what?
2, interest 2.
2 of CO2. You have 2 CO2.
Okay, so then
How
you
many
would
moles
take.
of water?
Yeah. So you would take.
So you always start with the given number, right? 2 mole of CO2.
Right.
And
Right.
then you multiply by ratio. That ratio, we know that is coming from balanced equation, but what are these?
So
It's
then you
like
would do it.
what is given, it should go down, right?
It'd be 1
CO2
mole.
is given, it should go down. What is
Yeah.
asking for H2O, it should go up. And then you fill the coefficient, these numbers, from the balanced equation. The balanced equation shows 2 H2O for every 1 CO2. That 2 times 2, that's going to give you 4. 4 of that
Right. Yeah.
H2O. Now, if the second question it says how many grams, as long as you know how many moles, then going from mole to gram it should be easy.
Yeah, you just convert.
You just convert to the to mass because you have now the molar mass. 18 grams of water is going to be 1 mole of water. So you want to change the mole, 2 gram, you multiply by the molar mass. Okay, so
Professor,
you want
would it be possible to open the exam?
What time is it?
10:17.
I think it's going to open at 10:30.
Okay.
And I just want to make sure that you all have taken the exam already with the honor lock. So yeah, it's going to start at 8:30. So just 10 more minutes. Sure. So we already talked about these.
Wait, we have another exam today? Did we not just have an exam like last week?
So if we have 1 mole of C4H10, we were trying to find out how many grams of CO2 would this equation gives us. So it's first you have to go from mole to mole of reactant to mole of product. And I would change that always mole of reactant to mole of product. Mole of given. For me, this is given and this is looking for. So go from moles of given to moles of looking for, and then answer the question. So you already have the moles of CO2. The question is how many grams? So in order to change from mole to mass, you need the molar mass. We had enough practice for CO2 molar mass already. So we know that 44 gram is mass for 1 mole of CO2. Then you can convert. So first you go from mole of given to mole of looking for. And then you're going to convert that to mass, because then you answer the question because you already have the mole. If you have the mole, from mole, you can go to mass, you can go to particles, you can go to, like when you learn about solution, which is a separate chapter for you, you can find the concentration, like the molarity. And for gases, you would find the pressure because you have the number of moles. You can use the gas laws to find volume, to find temperature, you find. So at least for now, if you have the mole, you can convert to mass using molar mass. You can go to particles using Avogadro's number. And mole for a molecule is not mole for atom. So we know that if you have 1 mole of this molecule, that would be 4 moles of carbon atom and 10 moles of hydrogen atom, being able to count them. There was another point for this slide, basically, is that if you end up with a fraction, after you balance your equation, you count number of carbon, you count number of hydrogens. So you have 4 carbons, so it should be 4 carbon on the product side. You have 10 hydrogen, so you should have 5 H2O on the product side. When you count the number of oxygens, it comes out to 5 plus 8, that's 13. For the 13 oxygen, since you have O2, you are using 13 over 2 to change that to 13 oxygen, but it's not, this is not common. You should not have fraction as the coefficient. You cannot have fraction as the subscript at all. So in order to get rid of this fraction, you multiply all coefficients by 2 to change this to whole number. So that was the point of this slide also, but I used that balance equation to give you another problem based on the stoichiometry of the reaction. So these are all balancing equation. If it's a compound that you have not seen before, okay, if it's a compound that you have not seen before, the formula should be given. But like aluminum acetate is something that you would expect to know from previous chapter, because in unit 4 you learn how to write the formula for aluminum acetate, and then you have the hydrogen gas. So basically the reaction is given in word, you convert to formula before you start balancing it. So you have aluminum, acetic acid, aluminum acetate, and hydrogen gas. Okay, this part, organic versus inorganic, don't worry about it. I think I already removed it. That was the last slide. I don't want you to be worried about organic versus inorganic. Is not part of this exam. I'm going to stop recording because the video is going to be too long.